We are working in the field of nanoelectronics. Effectively, we are working on semiconductor nanodevices, which we then cool down at very low temperatures in order to investigate quantum effects. You can think of normal transistors. Every mobile phone by now has 1 billion of transistors, which are rather big. And we take one of these transistors and we cool it down to minus 273 degrees Celsius, 0.14. And at that temperature, the transistor operates in a different mode. So practically from a conventional transistor, we get a so-called single electron transistor. So we can observe the hopping of single electrons throughout our device. And by applying proper voltages, we can really localize a single charge. In the next step, we apply magnetic field, and this magnetic field induces the so-called Zeeman effect, which practically means that you have a single electron, which its energy level without magnetic field is degenerate. So in physics, you speak about spin up and spin down. It's a quantum effect. If you apply a magnetic field, those two states are not anymore degenerate, so they have a different energy. And this two-level system is practically the main object we are studying in our lab. If you look more into the future, the idea is to use this two-level system for realizing a quantum bit. And in the group, we have already realized a quantum bit based on this system. So last year, we realized a germanium quantum bit, which we investigate. We try to understand how fast can we manipulate really our spin, and how long would the spin survive in one of the two states or in a superposition. Will this be useful for the future? Well, this is always the standard question which comes. There is the buzzword quantum computing, which is a dream of many researchers in the field. As I am a long-term optimist, a short-term pessimist, I would say it will work at some point, but it still might take a couple of decades until we are there. Effectively, we get nanostructures from our collaborators who are specialized in growing these type of materials. So we get a 4-inch wafer on which we have very small nanostructures. And just to give you a feeling, what does small mean? So many of our nanostructures have a height of a few nanometers, let's say 10 nanometers, and the width of a human hair has roughly 60 micrometers, so which is like 6,000 times the width of our nanostructures. So these nanostructures are very small, so in order that we are able to create devices out of them, we need to work in a clean room. And a clean room effectively is a clean environment which is dust-free, because as a human hair has a width of 60 microns, also a dust particle has a width of 10 microns. So if our device is a few nanometers, we don't want the dust particles fall on top of them. So we fabricate all our devices in a clean room. We use advanced machines like electron beam lithography, which allows us to write very thin lines down to 10 nanometers. And effectively, we create electrical circuits. And once we have those electrical circuits, we go back to the lab. And then the next step comes, which means we need to cool down our devices down to these very extreme temperatures. And we don't need just the very low temperatures, but we need also very high magnetic fields. So typically the fields we have in the lab, so we can go up to 9 Tesla. Well, I would really say it is the passion for fundamental physics. I think nowadays people always think about applications, but I would say when you work in basic research, it's not really that in your head when you go to the lab every day you have the long-term goal. You really have just fun by manipulating a single spin, things which are out of our normal logic, and this is really the driving force which allows us to go day by day to the lab even when things are not working. Because very often actually experiments do not work, and it might take a year or 1.5 years until one has a really nicely working sample. So one really needs to have a strong driving force and a lot of passion to continue and until the experiment works. Well, there are two main topics. The one topic is that of hole spin qubits. So we are trying to realize a quantum bit out of a hole. And what is a hole? A hole is like it's a missing electron. So you can think of a bottle of water, sparkling water. When you see the bubbles moving upwards, this is practically that the liquid moves downwards. That's the same concept in physics. So we have electron motion, the motion of many, many electrons downwards, which effectively makes a bubble moving upwards, and that's the systems we are studying. So we are studying holes in germanium on one hand, and on an even more fundamental direction, there is a prediction that there is a different type of qubit which should survive even longer. So qubits are very sensitive to environmental perturbations. So there have been theoretical proposals that one can create so-called topological qubits which would be protected by environmental perturbations. And in order to do so, you need to work again with semiconductor nanostructures, but now you need also to mix, apart from magnetic fields, also superconductivity, and the interaction between a semiconductor, a superconductor, and a magnetic field can create exotic states which are called Majorana bound states. So what Daniel is working on, Daniel works with germanium hole gases with the goal of realizing stable qubits which can be electrically manipulated very fast.
I am working on germanium hole gases, and my goal is to create a qubit in such a structure. So in general, there are different ways in how to trap electrons or holes, and what we do is we have a heterostructure that is a crystal made out of different materials, and in one direction we have silicon germanium, then germanium, and then silicon germanium, and this creates already in one direction a trapping potential for holes. And then once we have our heterostructure, we go to the clean room and then we pattern metallic top gates that are couple of tens of nanometers in width, and with those top gates, with the help of those top gates, we can create a trapping potential in 3 dimensions for our holes. And the goal in the end is that once we have such a hole trapped, we actually manipulate it with the help of AC, high frequency electric or magnetic fields. Actually, we hope that we can do it with electric fields, and with the help of this create a qubit, or maybe even 2 qubits next to each other, talking to each other and interacting with each other. The challenges here are mostly to really manage to make the gate structure in such a way that you can actually trap the hole, and trap the hole in such a way that it also stays coherent for a long enough time. The challenges here are, some of them we can control, some of them we cannot control so well, so it's also a lot of trial and error, a little bit of failure here and there. But in the end, what is really the driving force here is thinking about the fact that you can take the smallest, almost smallest, smallest particle that you can think of, an electron or a hole, and manipulate it in the way that you want to for up to seconds. So you can really control the quantum nature of that single particle for comparably long time. Obviously, the ultimate goal would be to have a quantum computer. As Georgios already mentioned before, it's probably rather hard to achieve in the next 10 years, but it's not impossible to think about it in the next 50 years. There are several approaches to that, but I think that spin qubits could have a major role in creating a quantum computer. IST Austria offers the possibility to take some courses that allow you to get a deeper insight into the field of quantum bits and quantum dots, and also superconducting qubits. And the collaboration between the groups here really allows one to get a deeper understanding in the broader field of quantum computation itself and solid-state physics.